It looks like it's us.
Do it.
There we go. All right. Well, thank you for joining me. Um, First ever Science Saturdays, and we're covering research and references. And so, why do I care? It's like the biggest thing. And I wish that we would have had people in attendance to talk about why we should care, because being informed can save you lots of money and quite possibly even your life. So this was, I thought, something that was kind of fun, interesting, not fun, terrifying maybe. The wellness industry is valued at over $2 million, and the wellness industry includes things like supplements, services, and wellness programs. The scary part is that none of this is regulated. And so there's no regulations that um, the wellness industry really has to abide by. And there's no real scientific studies that have to show or demonstrate that whatever it is they are claiming is actually true. So, one of the more prominent examples that I could think of that came right up to the top was ephedra. And so we had ephedra in the early 1990s. It was marketed as this miracle supplement, which is going to lose all the weight, right? But it was also killing people. And so it's not until people start dying that the Food and Drug Administration, the FDA, really kind of steps in and says, okay, we're done with this one. And then you can remove it. Um, but yeah, it was ephedra is terrifying, right? Now. And then the other really um, popular thing is like the fitness magazines that are at the end of every grocery aisle. They talk about, oh, lose weight fast, these different types of diets. And what they're doing is they're advertising to a want, which is lose weight fast, without any type of real scientific ground for why that should work. Um, and so when someone says research has shown, I ask you to consider, are they trying to sell me something? Is it a lifestyle, a service, product, or in today's day and age, clicks? And remember on that last point that influencers get paid for clicks, not for honesty. So if they go through and they say something outlandish, it's just like the fitness magazine at the end of the grocery store aisle. Somebody's going to buy it thinking that, hey, this is going to work. Somebody's going to click it saying, hey, this might be something that works. It's fast and easy, right? But most of these things aren't fast or easy. And this brings up the original influencer, Dr. Oz. So Dr. Oz is board certified in surgery. He's not a scientist. He's not a physician scientist. He is a surgeon. And he had his claim to fame on Oprah in the 1990s and really preyed on Oprah's weight loss journey through the advertising of miracle supplements, much like ephedra. I don't know if ephedra was anything part of the Oprah show, but he advertised things like acai berry extract and green coffee extract as miracle drugs. Um, so then, after quite a bit of ado, right, we ended up with the Dr. Oz show. And what was really interesting here is I stumbled across a peer-reviewed article that analyzed his particular uh, recommendations from his show. And what they found was over 50% of his claims were actually rejected by science or had absolutely no science to support any of those claims. And so Dr. Oz really is kind of that first influencer. He made his way and got paid for it without any type of real repercussions. And so here's that peer-reviewed research study. It came out of the BMJ back in 2014. All right, so going back to our presentation. Oops, give me a second. Um, then the question, when somebody says research has shown, say what research? If they say research has shown, but they provide you with no research, then that should throw up a couple of red flags. And so when somebody says research has shown, their job is to provide that peer-reviewed research, not a news article or a tabloid or somebody's personal blog. actual, real, peer-reviewed research, just like what I just got done showing in that article. So research, question is, where does it happen? It can happen in an academic setting. My personal experiences were with Northwestern University, Nebraska Medical Center, and Morehead State, Morehead. So even small undergraduate colleges like Morehead can run research programs. It can take place in industry. And so here's a couple of the more prominent industry settings that I've had the experience of either working with, collaborating with, or had friends wander off to. So AbbVie, Moderna, and Thermo Fisher are three really big names in the science field. And then, of course, we have the nonprofit setting. And so this includes things like governmental research at the NIH or the CDC. And a big question is why? And so why do people go do this research and spend all this time getting their PhDs? And when I was a PhD, this was something that had gone around, and I found it actually quite entertaining and refreshing. So why do people get their PhDs? Imagine a circle that contains all of human knowledge. There it is, right? So this is everything that we know, not what any one person knows, but collectively, what we all know. By the time you finish elementary school, you know a little. That's represented by that blue circle. By the time you finish high school, you know a little bit more. And with a bachelor's degree, you gain a specialty. There we have our nub. With a master's degree, we deepen that specialty. So now we've got a nice big dark nub. And reading research papers takes you to the edge of human knowledge. So now we're right up here on the very outermost boundaries of our collective knowledge. And once we're at the boundary, you focus. And then after you push the boundary for a couple of years, the boundary gives way. And that dent is that PhD. And so now, of course, the world looks a little bit different, but don't forget the big picture. And so there's small contributions that end up resulting in really big expansions in knowledge. And some of them are more influential than others. Some of them are more immediately impactful, but it all counts. And so a final note, keep pushing. So that was more of a two PhDs, like, don't give up, right? But let's see. There we go. So the people who are involved, the top of research is dictated by the primary investigator. We call them the PI. That's not a private investigator, primary investigator. So that could be a director, a manager, or in the academic setting, a professor. And they're completely and entirely responsible for the laboratory, including the safety training and education of all of the people who work for that person. And they are also the ones that come under fire in cases of fabrication and falsification of data and eventual publication retractions. And then often in the larger laboratories, there is senior staff. So these senior staffs can be PhD level or masters. Generally, they're long-term, and they're involved in laboratory management and troubleshooting. This is like the stable glue that keeps everyone together as PhDs come through and train. And then there's postdocs. These are recent PhD graduates, and they're training. This is a training period for whatever their next step may be. And then graduate students, bachelor's, masters, and they're there to learn, right? And then laboratory technicians, these can be bachelor's or master's level. They can be PhD level as well. And so there is no limit to who the laboratory technicians can be. And then there are undergraduate students, and these are the students who are just testing the waters, seeing whether or not research is something for them. And then in an academic lab, big groups could be 40 plus or more. This is my own personal experience in academics. Or it could be a small group that consists of a PI, a grad student, and just a tech. And so with biomedical research, it can really be divided loosely into three major groups. We've got clinical, which involves patients. There are translational, which includes animals and cell models of disease. and then basic science. And this is a question of asking, how does something work? This is science for the sake of science. This is where really big, great discoveries are made. Often, some of the most impactful research has been basic research that has led to a major discovery that then leads to an application. And so we're talking like Nobel Prizes, often are something that was started in basic research. And so these are kind of the people who are involved in each one of these. So in the clinical setting, often you'll end up with MDs, PhDs, nursing, and phlebs. Translational, you can have MDs and PhDs. And with basic, primarily PhDs. Not very often do you end up with MDs in that area because it's just not really an application. Um, yeah, that's right. And then each area of this type of research has a different purpose. And so clinical studies are generally there for like drug trials or medical devices. Really, it's the end for the applications of everything that came before it. Translational is one of the spaces that I worked in, and that's applications of basic research. So you know something has happened, and then you want to see if it happens within a given system. So this could be things like human disease in particular. Um, Oops, holy smokes. Sorry about that. Wrong button. And then basic research is very much discovery based. And so the things that are being investigated may not have an immediate practical knowledge. I was also involved in that space with mass spectrometry method development. So lots of fun, not a lot of applications until you get it all the way through and published. And so clinical, uh, once again, new therapies, it's very much hypothesis driven. Does this work? Does this not? Translational, that could be investigating things like new biomarkers. Do we have a protein that can be exploited to wipe out cancer, for instance? That's something that people are looking at with different immune system stuff. So using the immune system to identify cancer cells. So this could be both hypothesis driven or discovery. And then basic research, it could include things like new methods, new pathways, and this can be discovery or hypothesis driven. Big emphasis on discovery because you don't know what you don't know. So you just got to kind of look at everything and see if anything looks interesting. With clinical research, this is highly controlled, tightly regulated. It has to go through tons and tons of research or tons and tons of board review for ethical questions. And so you cannot involve patients without having some sort of ethical board review and say, yes, you are doing this ethically. So you have your whole idea of what it is you want to research. You bring that to your ethics board and they say yes or no. And that is to protect the researcher and the institute at which that research is being conducted. And then translational research, generally highly controlled, especially with those hypothesis-driven studies. And it's usually also tightly regulated if you're involving things like animal research or pathogens. So I was an HIV scientist. I had to go through a fair amount of ethical training for that. I also used human cells, ethical training for that. And so you can't just have anyone willy-nilly go and work on different viruses, right? So that's regulated. And basic research is also controlled because everything needs to be controlled. That way we ensure reproducibility and that we're not chasing things like artifacts, but generally doesn't require the same degree of like ethics board intervention because it's discovery and you're generally not working with like human cells, pathogens, or anything like that. All right, so a project is really just a collection of experiments that has been put together to make a story. And so within a lab, there's usually a theme. And so as a PhD student, my laboratory was focused on HIV and macrophages. That was the whole department, more or less. So that was the theme of the lab. I couldn't go out and look at like herpes virus because that wasn't anything that anyone was doing. So usually you're locked into a specific drug or a disease or a condition or a pathway. And that is kind of self-limiting because it's expensive to start up new avenues of research. And then research usually builds from those previous publications and training. So as a graduate student, my work was in mass spectrometry and the immune system. When I was recruited to do my postdoc, it was in mass spectrometry and the immune system, just a different set of immune cells. And so usually from that PhD, you're just continuing to build, similar to that diagram that I showed with the expansion of knowledge. And so it's really kind of neat when you start in your PhD adventure, you're continuing to grow in your expertise within whatever it is you originally chose. And there are opportunities to change fields, though it is a little bit more challenging. And then, um, so after you join a lab, you're sitting there, you're trying to figure out your own space. As a PhD student, you need to have a dissertation. What's your dissertation going to be about? And so you learn everything that you can about what this lab has done. And then you identify something of interest, and then you get to work, right? And then there's involved planning, testing, statistical analysis, and validation. And in the words of my PhD advisor, Dr. Siborowski, data leads to information, information leads to knowledge, and knowledge leads to wisdom. And that's generally kind of the theme of scientific research. So in academics in particular, it is publish or perish, meaning if you don't publish your work, there's no evidence that you did it. If you have no evidence that you did it, you have absolutely zero ground to stand on when you ask for money to do more, right? And so if you cannot gain funds for your lab will end up being shut down eventually. So a publication is a record of experimentation. And that publication must be written in a way that allows for reproducibility. I cannot emphasize this enough. There cannot be any secrets. You must write down all of your methods in a way that if Nikki's lab in Minnesota publishes his paper, my friend Owen out in Massachusetts can do it in his lab. He shouldn't have to come back to my lab to be able to do it. And that's really important because that gets to the heart of reproducibility. And if you don't have reproducibility, it starts to raise a whole bunch of red flags. Is this lab chasing an artifact? So is what they say happening actually real, or could it be a contaminant? Could it be something that was accidentally introduced? Could it be that the cell lines that were being used are just too old and they don't behave in the way that they were originally characterized? There's a whole bunch of different things that could go wrong. Those are considered innocent. But you also have fabrication, and so making up data. So if you don't have reproducibility, then the question becomes, is this data just made up? Did a postdoc or a graduate student just go through and insert data points to fit with whatever narrative they were trying to push? That's terrible, right? Or at the other end, you've got falsification. So that's data manipulation. That would be like the arbitrary removal of data points because they don't fit the narrative. And so both of those are really terrible things that could lead to retractions. And so reproducibility is absolutely essential, and that reproducibility must be obvious through clear methods in your manuscript. So then we have the whole area of peer review. And peer-reviewed articles are ones that have been reviewed not by friends, but the people who are considered peers. And what that means is that peptide mass spectrometrists, which is my training, review articles about peptide mass spectrometry, not RNA-seq, because science is huge, right? And so I need to be able to stay within my lane. So as a peptide scientist, I can review peptide papers. I also did protein mass spectrometry. I can review protein mass spectrometry. I am not a leukemia cancer biologist. I should not be necessarily reviewing leukemia cancer. And similarly, leukemia cancer biologists should be reviewing leukemia cancer biology, not Parkinson's disease. Those are completely different disease sets. And so this could be specific to a method or to a disease or just human health in general. So a publication generally follows the same formatting. You have an introduction, it sets us up with whatever background information we need to know in order to get to the point. Then there, in that introduction is going to be some sort of hypothesis. And so like, what is it that you're studying? What are you testing? And then we have those methods, and then the publication needs to have your data, and all of this data needs to be clear, concise, in a way that people understand it. And then we can draw conclusions on that data, and there's that knowledge section, and then discuss that data. So how does this data fit into the big scheme? And so this is also with the discussions, usually it also includes future directions. So what is the next thing that's going to happen? It may be something within this lab, or it might be in somebody else's lab. Like, this is, the discussion is a really great place to generate new ideas as to like areas of unknown. And so the data that should include things like experiments, statistics, and then also validation, because just because you saw something once or twice or three times doesn't mean that it's actually there. Validation is checking those results using a different technique. And so if I identify something with mass spectrometry, I need to go and see if that's actually there using something else. In my case, it's Western blot. You don't need to know it. It's just two different techniques. And then, like I mentioned, discussion, it really sets up a next project. It reveals more of the unknown. And then a publication also needs to include things like ethical considerations, whether or not it went through ethical board review. What did that board review look like? And then one of the most important things that have become quite popular is conflicts of interest. And so conflicts of interest must be disclosed. So just a little tidbit. This is mine. Nicole A. Haverland is who I used to be. So this is one of my publications. This is what this ends up looking like in its printed form. So we have this abstract. It's just kind of a synopsis of whatever it is brought up throughout the entire manuscript. Some people read, all abstracts are generally available so that you have a good idea of whether or not this is an article worth purchasing, or just to get, a general idea of what's going on in the article. Not all articles are required to be purchased. All of mine are available for free. And so here's that introduction, lots of information about the background, sets up the hypothesis. Then we have materials and methods. Like I mentioned, I was an HIV scientist, and so had to describe the safety considerations for working with a virus like HIV. And then the cell culture, the different mass spectrometry techniques, specialized techniques that were brand new at the time. And then validation techniques are over here, and then some of the statistical analyses are right over here. And so then you end up seeing this first figure. So data is generally represented in figures. I'm not going to go through what any of this means because it was a long time ago. But just now we are here. This particular journal has the results and discussions together. Sometimes they have results, sometimes they have discussions, sometimes they have results and discussions and then conclusions. It just is up to the formatting of the journal. So we've got some more figures. And then down here, this is one of the discussion figures that kind of wraps everything together. Conclusion is where we talk about what direction we were going in next. And then supporting information that's online. And here we have the important stuff. So the author information, who is the corresponding author? If you have questions, who do you reach out to contact? Acknowledgements, who did the work, who helped do the work, but maybe didn't do all of the writing. And so acknowledgements are important because it feels good to be acknowledged for the work that you've done. And then abbreviations, and then here is a note. The authors declared no competing financial interests. There's our conflict of interest statement. We weren't getting paid by any type of industry. This was done under an NIH fund. All of that information is also available at the top. And so the question that people should have when reading a research article too is, who funded it? Because that right there could be a financial conflict of interest. And then finally, the references. And so with this paper, I had over 60 references throughout the manuscript that talked or that set up the background information as well as the conclusions and discussion, and sometimes even the materials and methods. So if something has been validated as a common technique, you can cite that and say, we did it the same way, right? Saves on stuff. All right. So that's just something that that looks like. All right. And so with all of this, we build up to the infamous Andrew Wakefield MMR study in the Lancet. This is the study that linked or that attempted to link MMR to autism. And it was retracted in all of its awful glory. And it was retracted for a great number of reasons. It was not some sort of like hit job on this scientist. It was retracted for real issues. One, there was falsification. The data was misrepresented because a new syndrome was made up. And so uh, with the Wakefield study, they lumped children together as those that had uh, autism with bowel disease as a completely new syndrome. It wasn't children that had autism and children that had bowel disease. This was, in this paper, a new syndrome. There were also incredible undisclosed financial conflicts of interest. This study was funded by lawyers that intended to sue the vaccine manufacturers, and that's exactly what ended up happening. None of that was disclosed within the paper. There were also ethical violations where there was no real independent ethical approval. So you can't have your own ethics board within your lab, right? You need to have institutional review boards is usually what those are called. And what they cited was callous disregard for children. These children were receiving colonoscopies and lumbar punctures just to receive colonoscopies and lumbar punctures. There was no medical purpose for those outside of research. And then it was another piece was manipulated patient selection. These were not referred cases. These were recruited in order to fit whatever narrative they were trying to push. And so these children were recruited because they fit a certain expectation. All right, so then moving on, where do we find our references? So there are three really big areas for people to look for scientific literature. And these are the ones that I like the most. There are additional, like there's EBSCOhost and a whole great variety. What I find with PubMed, PubMed Central, and Google Scholar is that they're easy to use. So even if you don't have scientific training, you can dive in and start learning more about the scientific literature. So the first is PubMed. And this is hosted by the National Library of Medicine. This is what this looks like. You can say, all right, I want to learn about HIV-1, whoops, and macrophages. I type it in, I hit search, and I end up with 6,137 articles about HIV and macrophages. Now, that's a lot to sift through, so you usually want to use better filters than just that. All right, so then we have PubMed Central. Oh, PubMed. PubMed identifies articles that are both paid, so you may have to pay for access to those depending on how the research was done and what type of what the journal says as to whether or not this is a paid or a free to access publication. These also include international studies and historical studies. The difference with PubMed, so all of my research as a graduate student was NIH funded, and one of the requirements for NIH funded studies is that all of the research that was conducted, the publications had to be open access, meaning that we as a lab had to pay up front from those grants to have that fully open access, meaning that taxpayers are funding the NIH are funding labs, and then it needs to come full circle where taxpayers are then able to get into the research themselves. And so this is PubMed Central, very similar format, once again hosted by National Lab or Library of Medicine. Only difference here is that every single article that comes up is going to be open to look at. And then we have Google Scholar, which looks like Google. And so it's kind of neat here. So HIV-1 macrophages, same search, we've got 1,200,000. And so what's neat about Google is that it also includes patents, and abstracts. And so sometimes you can find some really neat information in different patent filings and the abstracts from different conferences. And so that's kind of fun. And then let's say that you're really interested in a author. You can click on that author and see what they've been up to. So usually, like I had mentioned, when you pursue your PhD, you end up in a specific field and then it's advancement throughout that field. So it's really beneficial sometimes to follow a specific author because they might have a lot of really great information from their entire career. Um, so yeah, click again. And then this is me. And so I have my own Google Scholar page. And so it's just something that's kind of fun. Obviously not near as nice as the last guy that I clicked because he only had like 14,000 citations. I have 851. So, and that's another thing too, is that's really nice with Google Scholar is you can see, and actually I'm going to bring that back up again. You can see how well accepted, loosely, how well accepted a specific paper is by the scientific community based on the number of citations. Now, this isn't always true because brand new publications are going to have zero citations, right? But as those papers continue to age, they should have citations. And so my top article was the first author was Owen Skinner. He was one of my friends from my graduate or from my postdoc. He wrote Top-Down Characterization of Endogenous Protein Complexes with Native Proteomics. It was kind of the first in its field, has 185 citations. And so it's been pretty well accepted. Whereas if we scroll down, sometimes you don't end up with a lot of citations, and that's okay too. All right. So we can all be scientists. So the really big lead up to hopefully this is kind of enjoyable, but we can all be scientists and maybe not a primary investigator, but we can all be data collectors. And so I've listed here a couple of the different spaces within Minnesota where we can be citizen scientists. And so we have the DNR, the Pollution Control Agency, the Bee Lab, and then if anyone wants to be a master gardener, you can be involved in the seed trials. So yeah, that was it. And now that we all have the same foundation of knowledge, let's have some discussion. No questions, no comments?
I do. I'm just organizing it. Yeah. Where does one even begin to start when claims like the vaccines cause autism?
Right.
Where does one even start to find it? Like where?
Right.
Step one.
Step one.
Because of all of the little specificities of science.
Yep. So great question. Question is, how does one even start with the claims for something like vaccines cause autism? And there is this thing called scientific consensus. When the scientific consensus, which is basically the vast majority of scientists, physicians are all screaming, no, they don't. That's generally the scientific consensus. And it's really unfortunate that people like physicians and scientists have been demonized in a way because they don't speak well with the general public in particular. Science is hard. It's hard to understand. And all of these people have incredible knowledge and background, right? But communicating that to people who don't, maybe they're specialized in something else, that gets confusing really fast. But when you have something that seems really simple, like vaccines cause autism, um, that is one of those claims that is hard to dispute because you're trying to show something that doesn't exist, right? And so one is to start by orienting yourself with the scientific consensus. And then it becomes, well, show me the evidence that vaccines do cause autism. And that's where it becomes a lot easier to show that, in fact, there might be this correlation that was represented in this one study, like the Andrew Wakefield study. Um, and so it's a matter of reorienting yourself in the question that you're asking, I guess, is to get to the heart of it. And so if you orient yourself with the scientific consensus and then say, okay, show me where autism does or is a result of vaccines, then it becomes a lot easier to dive into that research because now all of a sudden your hypothesis is clear. Vaccines do or do not. So the hypothesis would be vaccines cause autism. You can dive in, look at the research, and see, are those publications being cited? Is it a case study? A case study is a singular event, single patient, might be a couple of patients. With the Andrew Wakefield MMR study, it was 12 patients, and they were hand selected. And so we can start being critical of the methods that are being used within these controversial studies. But step one is to orient yourself with the consensus and then ask the question that is controversial. Does that make sense?
It does, yeah.
Okay,
Mhm.
cool.
Yeah, because there's a lot of them that you get these articles that pop up
Mhm.
and you're like, where do you even start to pick it apart?
Right. So Tylenol and pregnancy, that's another one. So the general scientific consensus is yes, women should take Tylenol if they're in particular running high fevers because high fevers are terrible for a developing fetus. So the scientific consensus is that Tylenol is safe because the alternative is not. Um, but it also has very little evidence to show that there are bad things that could happen to a developing fetus. And so it's to reorient yourself with the scientific consensus and then ask the question. But yeah, you're right. We do. We have a lot of conflicting scientific information out there. And something that has become really damaging is taking things that have a kernel of truth, because that can then become a really big thing. Well, look at this. This is actually true. Yep. So in certain instances, people do have, oh, here, good example would be like the COVID vaccines. So COVID vaccines are generally accepted as safe and effective. In a handful of people, people ended up with myocarditis. Well, if you stop that story right there, that's just like, oh, that seems really bad. It is. But the thing that isn't often said after that is that having COVID can cause myocarditis and at a much higher rate. And so if your fear is having myocarditis, then logically you should be taking that COVID vaccine because you could get myocarditis just from from the virus itself. And so these are the scientific consensus, right?
Mhm. So where would you find then that next, what part of the research then would you find that COVID itself causes myocarditis?
So
Where would,
right. So that goes back into diving into the primary literature. And that's something that I didn't talk about, had intentions of talking about. We have primary literature, secondary literature, and then everything else. So primary literature are the things like the commentaries and the original peer-reviewed research articles. So within the science realm, those are the ones that are doing the experiments. They have an active lab component. That is the research that you want to be looking at. If you're trying to guide these types of informed decisions, you might want to be looking at secondary research, which are things like opinions. So opinions don't have a uh, lab component, but it's based off of primary literature and reviews or commentaries. So those are often things where you're reviewing the primary literature to make some sort of message. And those are all published in journals as well. I don't know if I have any reviews. It's not something that I did, but I had colleagues that had some really excellent reviews about, one thing or the other. And that is also a place where people can go to get information about a whole general topic, but also like future directions, like, oh, this is a space where I want to be. What still needs to happen? Review articles are really great for that. And so the one place that you don't want to be is making those types of you don't want to be making those types of decisions or judgment calls using blogs or personal experiences, for instance, because there's no peer review component to that. And there is actually also a word of caution using news articles, because news articles are very similar to influencers now. They gain funds by people clicking and interacting. And so if that news article isn't linking to that primary research or secondary, so a review article or the peer reviewed, it should be taken with caution. And so if, a news agency reports, well, look at this, vaccines do cause autism, then they had better have all of that lined up clearly and concisely in a way that you can go through and get to that primary research in which they're basing all of their judgments, just like an opinion piece. So an opinion, a scientific opinion or a review article will also have all of those references very clearly stated so that you, as the reader, can go back and say, okay, well, is that actually what the message was supposed to have been? Because then you can go into that uh, article and say, well, that's totally not what I would have taken away from that, right? So everything needs to be traceable. And it's similar to like the Wikipedia rabbit hole where you can just keep on clicking.
Yes.
Same. So once you get, especially reading, especially reading online, when you are reading an article online, usually all of the references are hyperlinked.
Okay.
And so you can just go click, 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 click. And that's why it's important with news articles to be able to go through and go click, 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 click too. Because if they link to another news article and you go through that news article and there's still no primary research that's presented, that for me is always just kind of like, okay, if I care deeply about it, I'll go find it, but I'm going to be mad because that was their job. Yeah, angry typing. And no, I don't type like this, but it's angry typing. And uh then there's this erosion of trust. So, yeah. And that's part of the healthy skepticism in science, is always asking questions. It's not questioning the science, it's saying, well, where did this come from? And then, well, was it done right? Because statistics, too, statistics is a whole field that is crazy insane, where if statistics are done inappropriately, will give you a different message. And that's the emphasis. When done inappropriately, it's going to put you on the wrong track. And so it's making sure that you're consulting with statisticians when doing research. So usually there's always, when there's a primary research facility set up, there's always usually somebody who's doing stats too. And those are at least consulted with. And so I think like in my acknowledgments, I have some sort of statistician that I acknowledged. And maybe not if not that paper, because I had statistics so clearly it is generally part of any research or methods part of a paper is the statistics. And that is one of the best places to go as to whether or not somebody's going to have reasonable conclusions.
Where is there some sort of list somewhere of generally accepted things?
So that's fun question. Is there a place where things are generally, like where you can find the generally accepted things? So like the scientific consensus. Not that I'm aware of, though I really like Wikipedia. Wikipedia needs to be you need to have your healthy skepticism, because everything is put up there by people, right? And people have inherent biases. Sometimes we're wrong. But that's the beautiful thing about Wikipedia is when something is wrong, somebody can say, oh, no, that's wrong. Edit it, and there is this whole trail of evidence, right? And so when diving into something for the first time, something brand new, they've got, I'm sure, an entire page dedicated to vaccines and autism in Wikipedia. If they don't, they should, because Wikipedia has all of that kind of stuff, right? And what's really nice about Wikipedia is that they have the references at the bottom. And so as people go through and insert these different citations, they also include the link to get to wherever that information is. And so for me, actually, I used Wikipedia quite a bit to help what is, or orient myself with respect to what is the general consensus here as to, like, for me, it was HIV and macrophages, because macrophages are a small subset of cells that can be infected by HIV. But people don't talk about them because the ones that get absolutely decimated are T cells. Well, without T cells, then that's when you end up progressing into AIDS. Macrophages are important because as long as macrophages exist with HIV, there is no effective way to rid the body of HIV. So when I first entered my laboratory, I spent time in PubMed, Google Scholar, and also in Wikipedia trying to orient myself as to, okay, how do we navigate these waters? Because for me, all of it was brand new. And so as citizen scientists, I recommend actually going into Wikipedia with a healthy skepticism and following it all the way to the primary literature. And then once you get through some of those types of things, then you can go down the rabbit hole of PubMed or Google Scholar or whatever your choice may be.
It's funny because as a millennial, late millennial,
Yeah,
old millennial, I don't
right.
know. When I was in high school, Wikipedia was not an accepted source.
Correct.
That was one of the things that they taught us very
Yes.
specifically. And so I think I need to
So
We couldn't
reframe
even
that.
use internet in college as a source. I'm
Right.
not that much older than you guys, and my college was like,
right?
nope. We have a wonderful reference library here.
Right.
That's cool.
And so yes, so Wikipedia in and of itself shouldn't be the source, but it can be a really great place to get to where you need to be. And so just because Wikipedia says something doesn't mean that that is in fact the end all be all. Make sure that you get to that primary literature. What's cool about Wikipedia is that it can help guide that, because I like to say we don't know what we don't know. And Wikipedia can be really revealing in that way. Like, oh, hey, I didn't know that. Cool, click. And then, all of a sudden now you're into that primary literature. But no, there's no way I would use Wikipedia as the end all be all. But it is a really nice stepping stone.
Another question for you. So I work in education, and we often talk about the disconnect between educational research and educational practice. And I'm curious if you've experienced that with your work and if you have any ideas to address that hurdle.
So there's this disconnect between educational, and I'm only repeating this that way everyone online can hear it. A disconnect between educational research and educational practice. Same with scientific research and scientific practice. In the field of biomedical, it would be practical solutions to health and disease, right? Yes, there's big disconnect. And about the only thing that a person can do is keep pushing, because that is how we can influence adoption in education. It might be something like adoption of new practices. And so it could be, so one that I was reading about was a later start time for school, how kids apparently are doing better in school when they start at 9 o'clock instead of at 8 o'clock. And so pushing that time back. But that's not something that's easy to adopt because parents work And so there's this certain amount of pushback that and as somebody in the education field, my understanding of this might be completely wrong. So please stop me if I misspeak on that side. But the only thing that we can do is keep on showing the spaces in which, like, hey, this is really quite effective and it is worth implementing, regardless of the fact that there are new inconveniences that are being made. And so the same with science. Like in the science field, there are such incredible um, findings with respect to, like singular pathways and all of these different things, but without adoption into the medical field, we're limited on how we treat disease in particular. So, as a postdoc, I was working in B cell biology. And so it was understanding B cell development, maturation, activation, and eventual transformation. So, how B cells grow, how they do their job, and then what happens when they transform into cancer, generally leukemia and lymphoma. And one of the leukemias that was of particular interest to me was chronic lymphocytic leukemia, CLL. And there is so much science out there that indicates that we're treating, generally speaking, not everyone, but we're treating CLL inappropriately because there are distinct subtypes. And if you don't go through and identify what subtype of CLL a person has, they may have absolutely disastrous outcomes, even though treatments are available. So why aren't we doing that? Same with like skin infections. Why aren't we taking a swab to see what are we actually dealing with instead of saying, hey, this looks like a bacteria. It's actually a yeast, which is a fungi. You can't treat those the same. And sometimes it works because for the vast majority of people or occasions, that probably is a bacteria. But in those subsets of people that present abnormally, when we treat them with an antibiotic instead of an antifungicide or a fungicidal, um, you're setting them up for a world of hurt. And all it takes is a skin test, right? But that costs money and it takes time and all of these different things. But like, one of my shows that I was watching when I was going through my PhD and after was House. And it was always fascinating to me when something got messed up because they were doing just the standard uh, care, right? Just standard care. And one episode will always sit with me about how all they had to do was look at something under a microscope and they would have seen it immediately, but they relied on different types of technologies. And yes, this is dramatized for the TV, but it does in fact happen. And so, as we continue to treat people with that standard care instead of considering specialized subtypes, um, that standard of care won't really improve. And like people's understanding of things like cancer. So we've spent years and billions of dollars in cancer research, right? Except for the thing that a lot of people don't recognize is that everybody's cancer is completely and entirely personalized. So we could all end up with CLL, and each one of ours is going to present completely differently because each one of us has a unique genetic code. And so we're kind of limiting, uh, we're self-limiting, I guess, because it's easier to lump things together. And it's really hard to identify that, we have subtypes of stuff. We have subtypes of CLL, just like we have subtypes of ADHD. We've got subtypes of autism. We have subtypes of just about everything. And when we fall into the trap of treating everything within that little piece the same, that's when we can end up with less than ideal outcomes for treatment. And so, yes, we do experience it. Very long-winded way of saying, yes, it is experienced in science. As a scientist, I am incredibly frustrated with the lack of translation into the clinical field, treatment, care, or treatment programs, those types of things. But it's hard to adopt. And then when things go wrong, let's say that something does get adopted and something goes wrong, then all of a sudden there's the lawsuits that are involved and all of the fallout. And that's happened many times in the medical field too. So there is this resistance to adopting or moving outside that standard of care, in part because of fear of what happens if this isn't the long-term solution to something. Hi there.
Hey.
Where you headed?
Well, I'm trying to find
The
a
book?
book to buy because
There we
we're
go.
leaving.
Well, perfect. Welcome. Right behind you. So yeah, that's that. Let's see. Do we have anything online? Nope.
Is there any movement toward doing more research on wellness ads,
Oh.
etc.?
That's one you could be tried against.
That was the big issue. Talked about that at the beginning.
Oh.
Yes. So at the beginning, we talked about the wellness industry, and the wellness industry is a multi-trillion-dollar industry just in the United States, and none of it is FDA regulated. So if depending on your own morals, ethics, and values, I could push out a supplement that was just pure sugar and say, hey, it's going to make you lose weight fast. It has elderberry juice in it, and it doesn't have to because nobody's checking. So over-the-counter vitamins and supplements don't have to adhere to any type of standard because they're not being tested. And that's how some lawsuits have come up in the past. I don't know if you recall, quite a few years ago, I'm sure, the generics, there needs to be a certain amount of like, yes, this is here, but then there is this confidence interval as to how much over or under you can be. And when advertising a generic for like Flintstones multivitamins, you have to have more or less what you say is there. And I can't remember, but there was a couple of big corporations that came under fire because their generics did not have what they were advertising. And so there is some regulation there. I know that it's not regulated like our over-the-counter medicine, where generics have to be within 90% effectiveness to their name brand component. But yeah, like, I don't know, because the question is who's going to fund it. So sometimes you'll have labs. So there's ethnobotany, really cool space in science where they're looking at like natural products that are produced. Let's say dandelion. Dandelion has apparently all these medicinal benefits. I like dandelion tea because I like dandelion tea, not because it's been advertised to do anything for me. But ethnobotany is an area where people are funded to do research on some of these old medicinal herbs because they had some value in with indigenous populations or cultural things where they were brought over. And so there is a space for it, but there's not a lot of funding for it. Not to say that that's right, wrong, or otherwise. I personally think that we should be funding things that have a long history of being used for medicinal purposes, just to establish whether or not like they were on the right track. The placebo effect is a real thing, but sometimes, I mean, acetaminophen is a natural product derived from, I think it was a bark of a tree or a root. And so like it was originally in one form that can now be chemically produced and put out with a certain amount of purity. And don't hold me to that, but I think it was acetaminophen. So
I know it's interesting. I sometimes, my mom's like, oh, they're putting me on blood pressure medication. So I can't eat pineapple anymore.
yes, yep,
And I'm like, why can't you eat pineapple anymore? She goes, because it lowers my blood pressure.
yep. So
you were eating pineapple, or you were eating grapefruit every day. Maybe even a couple of times a day because of how your mother was and
right,
how you adopted it, and you like grapefruit.
yeah.
Now you have to quit eating grapefruit that lowers your blood pressure to
Right.
go on medicine that will lower your blood pressure.
Right. So what she's describing is a boost. And grapefruit juice, actually a lot of medications you cannot take with grapefruit juice in the belly. And that has a lot to do with the different enzymes that are present in grapefruit juice that will speed up the breakdown of some of those drugs that are supposed to last for a long time. And what you don't want, for instance, is with blood pressure medicine, you don't want it all to break down super fast because then your blood pressure is going to crash, and that's a bad deal, right? So you don't take any type of grapefruit juice or grapefruit juice supplement. And so being conscious of what it is you're putting into your body, in addition to whatever else, is really important because in that case, it's an expedited breakdown of a long-acting drug.
Well, that
Yep.
was pre-drug though.
Oh, yeah. Yep.
'Cause,
Well, grapefruit juice has been touted for a whole bunch
That's
of
what
stuff.
I'm going with,
Whether
like, there are things out there
Right.
that do what we need them to do, but
Yep.
there's no research out there to
Right.
support.
And
to quantitatively place that,
Mhm.
okay, if you want to do this via grapefruit, you need to drink 4 ounces every half hour,
right. So in my experiences in the sciences, something that I had noticed is that
Yeah.
funding is pretty specific for disease. It's not for the basic sciences where that actually would fall. So the NSF, the National Science Foundation, funds primarily basic science, not applications, not translational, not clinical. That's where that is. But those funds are minuscule in comparison to NIH funds that are, heavily competed for, but those are primarily for disease states, methods development to understand disease states, those types of things. But researching pineapple juice or grapefruit juice or anything like that as it pertains to a healthy human body, well, for one, it's going to be a really hard study to do because you're using human people, and human people are so reliably unreliable. That's part of the failures in clinical research. And yeah, it's there's a very small space for something like that. And um, there are companies, so some of our industry partners like to fund basic research too. That's also where that importance of financial conflict of interest comes in. Those types of disclosures are really important because if you are funded by AbbVie, people need to know that because then they can really go through your research with fine tooth comb, because it's really important that you don't go through and make your story about how this AbbVie product does what it's supposed to, even if it doesn't, right? That goes into the falsification and financial conflict of interest. But there are industries out there that will fund some of those things in labs because then they can commercialize it. And so let's say that you're interested in, this extract from a South American tree. They can fund that in a lab that is already known to do that type of research. And then the benefit for them, for the lab, is to have secured funding, but for the industry is the potential for commercialization of a product. And then they can say, look, research shows. But then it's a question of, is that moral? And then it needs to be even taken further. Independent research shows, so that's not funded by that organization, that's separate labs, all of the stuff, making sure that this is reproducible across labs as it pertains to a specific product. What's really cool, and what I kind of am leading into, is natural products. So one part of my postdoc lab, not anything necessarily that I was involved in, but one part of my research lab was natural product discovery. And natural products are generally those ones that are top interest for antibiotics in particular. And so right now we're running out of antibiotics that are effective because our bacteria are gaining resistance to our most common antibiotics. And so what we really need is a whole new class of antibiotics that will then be able to eliminate these different pathogenic bacteria. And so that space is natural products. And so like the discovery of penicillin was an accident. It was fungi landed on top of this bacterial plate. And what they noticed was, oh, hey, look, whatever this this fungus is producing is preventing growth of this particular bacteria. Ding, that's penicillin. Really cool, right? And so you can look at natural products that are produced by fungi and by other bacteria, actually, to see whether or not we have any potent antibacterials that can be used. And so some industries will fund that type of research in hopes of being able then to commercialize whatever that product might be. But it's hard because all of the low-hanging fruit has been picked. So, what do you think? We've gone over. Have any other burning questions? I thank you both for showing up and our friends online, mostly family.
Yeah, that was really interesting.
Did you learn? The big takeaway should be don't trust influencers. That really if I can emphasize anything, please just don't trust influencers.
I think there's just a lack of trust in general right now.
Yes.
in everything.
There's a skepticism, and yep, the more it's uncomfortable to admit when a person doesn't know stuff. It's uncomfortable to say, hey, this is not my expertise. And when people then get up in front of other people saying, hey, we can't trust this, it's easy to say, yep, can't trust this. And so we have this skepticism that has grown, and I say healthy skepticism, but now we have hit the point where it's unhealthy skepticism, where general scientific principles that have been built over decades are being questioned. Like I ended up in a space where they're questioning the existence of viruses. Excuse me, what? And that is now in the area of unhealthy skepticism. I worked with viruses. Can you see them with a microscope? Nope. You can with certain technologies. But I know those viral proteins. I was able to image where these viruses were based on the expression of those viral proteins. So like I could look at my petri dish of human cells that were infected with HIV and say, hey, look, I'm at about a 90% infection rate. Okay, neato, let's do the analysis. But to have people actually questioning the existence of things that is a scientific consensus. Viruses exist, period. COVID is real, period. Now you can question the effectiveness of those mRNA vaccines, whatever, but to deny that that exists is absolutely beyond a healthy skepticism. Because yeah, like, so basically don't trust influencers. Don't trust the people who are trying to make money off of it. If they're trying to sell you something, chances are whatever it is they're saying may or may not be true. That's where healthy skepticism really is. So. All right, cool. Well, thank you everyone for tuning in. Till next week.